So, look at it for a second before I talk about it. So you've got, I'll circle my answer so you can tell what my final answer is. Now, the way that you simplify these may be slightly different than what I've done, or at least on whether you decided to do fractional exponents or it just depends on the problem and what you're doing with it. So if it's free response and all they're asking for is f prime, you can leave this line right here. You don't even have to try to put the 1/2 and the 3 together, although it looks better if you do. It just depends. Now, one reason that I like to do that, for example, on number 3, let's say that they're asking you to find like a maximum or minimum. And if they're asking you to find maximum or minimum, you have to take the derivative, set that equal to 0, top and bottom equal to 0, find your critical points. So it's a lot easier to find critical points when you turn it back into a fraction than if you don't. But as far as like a standard way to leave your answer, it doesn't necessarily matter. I tried to go with something I thought they would probably put on a multiple choice answer choice for these, which still isn't a guarantee. Sometimes they use negative exponents. Sometimes they use fractional exponents. There. Sometimes they would take this and turn it back into a root instead of that. So remember, this is a review on chain rule. Okay, so remember when we're doing chain rule, first of all, like for number 1, it is going to be easier to deal with this if you think of that square root as a 3x minus 4 to the 1/2 power. So what we're doing there, whenever we're doing chain rule, is we're saying we got like an outside and an inside function. So my outside function is that stuff that's being raised to the 1/2 power. The inside part is the 3x minus 4. So when we take the derivative using the chain rule, we take this 1/2 power and we just take the derivative. We multiply out front by 1/2. We subtract 1 from our exponent to get a negative 1/2. We leave the stuff on the inside exactly the same, right? And then we must multiply by the derivative of the inside. So we multiply by that 3 right there. And then I combine the 3/2 there and then sent that root back down to the bottom on that. So like whenever we're looking at number 2, our inside part is the pi over x. Our outside part is the cosine. The 3 is just a coefficient, so it kind of hangs out front. So the derivative of cosine is negative sign. I went ahead and put the negative in front of the 3 there. I left the stuff on the inside, the pi x, alone. But you must multiply by the derivative of the stuff on the inside, which is just pi. And then I did pull this back up here with the 3 because that's typically where you're going to see it for that. It's been a little while. I was like, as I walked around, if you were feeling like you were a little rusty and couldn't remember how to do this, you were not the only one, because there were several of you that were, glitching out a little bit on this stuff. This is one I probably need to like bring back up more often, because chain rule is one that's hard. So 3 does not necessarily have to be done with a chain rule. You could do a quotient rule for number 3. However, if you take this stuff on the bottom and move it up to the top of the fraction and give it a negative exponent, then it's much quicker to do a chain rule than it would be for the quotient rule on that. So again, here you're looking at outside stuff is being raised to negative 1 power, and your inside is 3x squared minus 4x. So you multiply out front by that negative 1, subtract 1 from your exponent, leave the stuff on the inside alone, then multiply by the derivative of the inside, which is the 6x minus 4. And then I just sent the negative exponents back down to the bottom there. For that, I just left my negative out front. You could also distribute that negative if you want. And you could use a chain rule for the last one, but I just decided to say that this is x to the negative 3 over 2, in which case you're really just using the power rule. But as you can see, I had some trouble with that because the first time I did it, I forgot my negative right there. And so I got this, which is wrong. And then I fixed it and started to fix this, but I added 1 to the exponent because what was I doing? I was trying to integrate, but that's not what I've been asked to do. So I marked that out, and then finally I multiplied out front by the negative 3 halves, subtracted 1 from the exponent to get negative 5 halves, and sent those negative exponents back down to the bottom, which was what I was supposed to do. So, and this is one, especially on the more difficult problems, it's easy to, even on like simple power rules, it's easy to integrate instead of taking the derivative now that we know how to do both. So watch out for it. Okay, questions? So all of that is the stuff that we have done before. Those are derivatives. What we're looking at today is how to go backwards, because we've not done anything yet that's sort of like a chain rule sort of problem, right? Everything we've had has been power rule, or we've tried to set it up so it's like a power rule. So, what we're going to do is we're going to use integration by substitution. Okay? So, if I have, I messed this up. This should have an integral symbol in front of it. Add in an integral symbol right here. If we are integrating a composite function, f of g of x, that means like a function inside of a function, right? Then the only way that we can do it is if we have f of g of x times g prime of x. Because think about taking the derivative. When you take the derivative, you take the derivative of the outside function, you leave the inside function alone, and then you multiply by the derivative of the inside function. This stuff right here looks like the answer to the derivative of a composite function, right? Like, in fact, let me write it out. I should add that. Like, if we had the derivative of f of g of x, actually, let me make that a capital F right there. And in this case, the derivative of capital F is lowercase f. So if I am doing this problem, my outside part is my capital F, and my inside part is my g of f, or g of x, right? So if I'm taking this derivative, what is the derivative of capital F? We just said it was going to be lowercase f, and I have that written down here so we know for sure that is the case. Or we could call it capital F prime, but we're going to use that lowercase f, right? And then I got to leave g of x alone. And then what do I have to multiply by there? G prime of x. So notice the derivative of f of g of x is this. That's our chain rule, right? This is the chain rule. And the answer to the chain rule problem is what we've got to have if we're going to integrate, right? Notice how those are the same. And then if we do integrate, we'll get what we started with plus c, right? Because any coefficients get taken away. A little bit of a simplified version here that uses a u instead of a g of x right here would look like this, where u could be your g of x. So u can be 2x squared, or u can be x minus 4 there. So f of u, and this du is your derivative of u, equals capital F of u plus c. So what we're going to want to do here is we have to find the inside part of the function and use some substitution to turn it into this easier form right here. So best way to do this is just to jump into some problems. So in this case, I've got x squared plus 1 squared times 2x. Now you do have an option right here to expand that, right? Because we could do x squared plus 1 times x squared plus 1 times the 2x. You could expand it and just use the product rule. However, they're probably not going to do that. If this is multiple choice, the answer choices are not going to look like you did it with the product rule. They're going to look like you did it using u substitution, which is what we're going to do here. Even if you did expand it, then you're going to have to like factor your answer back out at the end, which might be really difficult to do. U substitution is the way that we want to go on a problem like this. So what we want to do is think about what probably would have been the inside function if you were using chain rule to take a derivative. And so looking at that, what looks like it would have been the inside part? Not the 2x. It's going to be this x squared plus 1. So a lot like when you're like taking a derivative, like if you have something raised to a power, whatever's inside of that being raised to a power, a lot of times is what you're talking about. When you have trig functions, whatever's on the inside of the trig functions, a lot of times is that. So we're going to take this, and I'm going to say u equals x squared plus 1. Now, what that means is now I could instead say that I've got the integral of u squared. But I still have times 2x dx right here, right? And I cannot integrate unless everything matches, unless everything's the same like letter, right? So what we're going to do every time is we are going to take the derivative of our u. Okay, if I take the derivative of u with respect to x, I'm going to have du dx equals 2x. Everybody good there? Just using power rule to take the derivative. Now, I need to have an integral of something with u's, and I need to have a du out on the end, right? I can't have like a du dx. But right here where I have du over dx, would it be okay for me to multiply this side by dx and cancel it out, and then multiply this side by dx here? That's a rule that we can use, right? We can multiply both sides by something. So now I'm getting that du itself equals 2x dx. Now this is convenient here because do you see this anywhere else? That's right here, right? So that means this expression could be replaced with a du. So now I've got u squared du. Now, if I had given you that problem, the integral of u squared du, on your homework last night or the night before, could you do that problem? Yeah, we know how to do it, right? So this is just, now what we've done is we've turned this into a power rule. So we can integrate this. So to integrate, we're going to increase our exponent by 1. So we get u to the third. We divide out front by that new exponent, so we get 1/3. And in this case, since we do not have limits on our integral, we do not have a definite integral here, we need to put a plus c. Now, it's still not going to be your answer. But if we think back to what we started with, u equals 2x plus 1. So that u right there, we can just put 2x plus 1 back in. So we can get 1/3 times 2x plus 1 cubed plus c. Oh, yes. Why did I put a 2x? Gosh, I shouldn't element erase right here. I don't know why I took a derivative there. X squared plus 1. And this is our answer. You can check your work on these pretty easily by taking the derivative, right? So if you take the derivative of this, and you're wanting to check your work, right here you're taking the derivative of 1/3 times x squared plus 1 to the third plus c. You would multiply out front. 3 times 1/3 is just 1, right? Then you have x squared plus 1 to the second. And then you would multiply that by the derivative of the inside, which is 2x. Now the dx is part of the integral there, so that's not included in like your answer, but this lets you know, oh wait, that's what I started with. I'm good. Right here. Okay, questions? So if you start off picking the most difficult thing on some of these problems is picking the correct u. Sometimes it is very difficult to tell what the u is going to be. If you get the u, then you should be able to rewrite it so that it's just a simple power problem, and then at the end you plug back in. Now, some are much easier to find u's than the other. So if I look at the next one, what do you guys think the u should be on that problem? 5x. It's the inside stuff right here. All right. So u is 5x, which means du dx is 5. Now, a lot of times I like to kind of skip this step because every single time you're going to multiply both of these sides by dx so that you just have a du. So a lot of times I don't write that middle step. I skip all the way to the du equals 5 dx. I go ahead and multiply that dx over there. So I know my 5x is the u. I need a 5 dx. Do I have a 5 with my dx? I don't, but could I put 1 with it? Can I take this one right here and just like move it over here? That would be okay, right? So like I'm going to go a little overboard right here, and I'm going to actually rewrite it. I don't usually, but I've got cosine of 5x, and then I'm going to move that 5 over here with my dx. So what's happening here is that this right here is my u, and then this stuff right here is my du. So that will look like this, the integral of cosine of u du. You must have that du in order to integrate, right? So if we were missing the 5 dx, then we couldn't proceed, right? But it was there, so we're good. Now we should be to something much more simple. What's the integral of cosine of u? Is sine of u plus c. Right. Derivative of cosine is negative sine. Integral of cosine is positive sine. Right. Signs are opposite. So whenever we integrate here, now I've got sine of u plus c. Only thing I've got left to do is plug your u back in. So I'll have sine of 5x plus c. That'll be my answer. Okay, questions? All right, let's keep going. Oh, did I not put an example 4 right there? I didn't, did I? I was working on this kind of late last night. Usually I do 4 days on this. I've got it down to 3. So I was pulling from some different places, and clearly I didn't finish that. That's okay, we won't have time to do it anyway, probably. So, all right, here we go. In this case, what do you think the u is going to be, the inside part? X squared minus 1. On the first 3 we've done here, it kind of works like it does chain rule. If you got something inside of parentheses and something's happening to it, that's usually your u. In fact, today, I don't know if we'll see anything that's going to be that difficult to find the u for. So the u is x squared minus 1. So the derivative of that, I'm going to do this. I'm going to do du. I'm not going to do du dx. I'm going to skip a step here. What's the derivative of x squared? 2x. And I'm going to go ahead and put the dx over here on this side. Now, this is my u. This part right here is my du. Do I have those pieces? The pieces that I need. I've got the dx, that's there. It's pretty much always going to be there. I've got this x out front. What am I missing? I need a 2 to go with that so that I have the full du. The full du has to be there in order for you to integrate this. I really just needed 2 right there. If I had a 2 right there, I'd be okay, right? In fact, I can put a 2 right there. No, we don't want to go that direction. You're thinking the right thing, but if I have a 1/2 du, then I end up with like a fraction on my integration, which I guess we could do it that way, but it usually is going to like introduce fractions into your integration that's going to make it more difficult. So instead, what I would do is like try to get this to match exactly, because I can put a 2 here as long as I put me a 1/2 out front, right? Because 1/2 times 2 is 1, right? So if I put both of those there, then I have an integral that I can integrate. And if the 1/2 is all the way out front, Michaela, where we don't have to worry about it, it makes it a little bit easier. Although, I mean, really, as I think about it more, you could do it that way. You could say, oh, I've only got x dx, which is half of du. And then you could still like take that 1/2 and pull it out front. So it could work that way. That would work too. That's not usually the way I do it, so my brain was having to process that a little bit. So like what I'm looking at now, I've got 1/2. I'm going to write it this way. X squared minus 1 to the 3rd power. And I'm going to put this 2x dx over here. You don't necessarily have to write this step, but because we're just learning this, I want to be really clear about what's happening here. So I know this stuff right here gets replaced with u, and this stuff right here gets replaced with du. And so I've got 1/2 the integral of u to the 3rd du. Everybody good so far? Okay, so I'm going to just leave the 1/2 out front. It's a coefficient. I don't have to really think about what's happening there with it. I'm going to integrate u to the 3rd. So that's going to be u to the 4th. I'm going to divide out front by that new exponent. So that'll be a 1/4 right there. And then I'll have a plus. I could put the plus c on the inside or the outside of my brackets. Right? I could have this, or I could have 1/2 times 1/4 u to the 4th plus c. It kind of doesn't cancel. Well, it doesn't cancel. They will stay because you don't have limits here, so they won't cancel each other out. If I put the plus c on the outside, that's fine. I get 1/8 u to the 4th plus c. And then I would need to plug that back in. I'm just gonna put the answer up here. I'd have 1/8 times x squared minus 1 to the 4th plus c. That's going to be my final answer, right? Because I take that u and I replace it back with the x squared minus 1. du, it's not mathematically correct to say this, but it works. Du kind of gets replaced with the plus c. So the du must be there because it tells you what you're taking the integral with respect to, and if you don't have it, it's not going to work. You can think of it like du gets replaced with plus c whenever you integrate. Although technically, mathematically, that's not what's happening, but in practice, if you are thinking of it that way, you'll get the right answer. Now, what if I put the plus c on the inside of my brackets there? Then I should have to distribute, right? And then I should get 1/8 u to the 4th plus 1/2 c. Which is different, right? But what is c? It's an unknown constant, right? So c is an unknown constant. So if I have half of an unknown constant, it's still unknown, right? Like I don't know what it is. So whenever when we're doing any math right here, where we're dealing with this like plus c, this is still an unknown constant. So anytime you do any math to a plus c, you can just turn it back into a c. It just like absorbs whatever you try to do to it, right? So if you multiply it by 7, and you have 7c, it's 7 times an unknown number, which is still just an unknown number, right? If you multiply it by 1/2, if you know, anything you do to the c, it can sort of absorb and just stay a c. So I usually just put the c way out here on the end, like that, instead of this, so that you don't have to worry about distributing anything to that c. Okay, questions? Whatever I meant for us to do for example 4, we're clearly not going to do because I didn't put a problem there. Let's look at time. Yeah, we need to do that one. Okay, we're okay because the e's are pretty quick. Example 5. I would, on this problem, well, you can do it now, you can do it later. I would, before I do anything, I would change this to a negative exponent. I would write this as the integral of 3x minus 5 to the negative 2 power. You could also do that later, so it doesn't necessarily have to be done right now. I find it a little easier to do it right now. What does it look like the u should be in this case? 3x minus 5. So if u equals 3x minus 5, the derivative of 3x minus 5 is just 3, and I'm going to go ahead and put the dx over here with it because I'd have du dx, and I'd multiply both sides by the dx. So, I'm close, but what do I need with my dx? I need a 3. Can I just stick a 3 right there? I can, as long as I put a 1/3 out front. So if I do that, then this part right here gets replaced with u. This part right here, my 3dx, that gets replaced with du. So I'm looking at 1/3 the integral of u to the negative 2 du. Okay. Now we're just power rule. We just got to integrate using that power rule. So I'll increase, well, 1/3, just kind of let it hang out front. Integrate by increasing your exponent by 1. That gives you -1. You're going to divide out front by -1, which really just gives you a negative out there. And then I like putting the plus c over here on the end. So we'll have -1/3 u to the -1 plus c. And now all we really have to do is plug our u back in. So whatever the u was comes back in now. -1/3 times 3x minus 5 to the -1 power plus c. They might leave it like this. They might do 1 over, let's see, we'll need a negative out front. -1 over 3x minus 5 plus c. You could have that to the first power, but you don't really need to write something to the first power. No. I messed it up. This will have a 3. Yeah. Like that. Chance they may even distribute that 3 in the bottom, but I'm just going to leave it. Okay, it's making sense. So, like, most of your homework is going to be dealing with problems like these, where it's sort of like a typical, like, chain rule sort of problem where you have something raised to a power. We also are going to see some exponentials in here. And exponentials always throw us for a loop because we kind of panic when we see them. But when it comes to derivatives and integrals, they're really almost the easiest ones to deal with, right? Because what is the derivative of e to the x? E to the x. What is the integral of e to the x? E to the x. But you'll notice here on example 6, we don't just have e to the x, right? We have e to the 3x. So this has a tiny little u substitution built in, right? So what should be our u for this first problem? It's going to be the 3x. What's up there in the exponent is your u. So that means du, what's that going to be? 3, and then we'll put that dx with it where we move that over. So do I have the du that I need? No, I just have the dx. But can I just add a 3 in? As long as, like on the last problem, I put a 1/3 out front. So I can put my 3 right here. As long as I also put a 1/3 out here. And so now this part right here is my du. And this part right here is my u. So my new problem looks like this. 1/3 integral of e to the u du. And this is what makes these kind of easy. What is the integral of e to the u du? E to the u plus c, right? So we got 1/3 e to the u plus c. And now we can just plug our u back in. So I've got 1/3 e to the 3x plus c. Does that make sense right there? Mm-hmm.
So when you have 1/3 integral of e to u du, and then you have 1/3 e to u plus c, so plus c to du.
It's not technically mathematically correct to say that, but if you think of it like the du, the plus c replaces the du when you integrate, then that will work. Yeah. So whenever you integrate, the du is going to go away. and the plus c appears. So you can think of it like that du gets replaced with that plus c. Although technically, mathematically, that's wrong, but you'll get the right answer if you think of it that way. Okay, last one real quick, because this one is a little bit different. Right here, and we won't, well, I said last one. We won't get to that very last one. That's okay. It's not actually a u substitution problem anyway. So u, in this case, is going to be x squared, which means du is 2x dx. What's the problem here? I got a dx, I got the x that I need. I've got a 5. I need a 2, right? Everything has to match perfectly. The way I like to deal with this is I just take this 5 and I put him out here. Let's get rid of the 5 here. Let's put you out here. You're in my way. Put you outside, right? Now I've just got x dx, right? And you can do that with coefficients. You cannot do it if it has a variable. Like I can't take the x outside. But with coefficients, I can do that. So now I've got x dx. What extra do I need? 2. So I'm going to say I'm going to put 2 right here. And then that means if I multiply by 2 on the inside, I've got to multiply by 1/2 on the outside. So rather than thinking of what I've got to multiply by 5 to get to, I just pull it out of the way and don't have to think about it that way. So now what happens is that I've got 1/2 times 5, which gives me 5/2. And then I've got all the stuff right here, my 2 and my x and my dx. All that stuff right there is your du. So you've got e to the u du. And now we're just down to, like we had on the last problem, we got 5/2. When we integrate e to the u, we just get e to the u. And then we put a plus c over here on the end. And then we plug back in. So we got 5/2 e to the x squared plus c. Okay. Very quickly on this last one, this one is not all of these. You're going to see one of these on your homework. Not all of these are u to u substitution. You would need to love connection. Yes. Also, we have not done with differential equation stuff yet, but here's what happens. Multiply both sides by dx. Now we've got dy equals x plus 2x squared over the square root of x dx. And then you integrate both sides. When you integrate dy, you just get y. And then over here, you've got an integral problem now, right? So you would work that out and love connection, that problem. So when they give you, say, solve a differential equation and it says dy dx, it's really just saying to integrate that stuff over there on that right side for that. So your homework is from the book. You have these problems here. A note on number 15, because I remember this being an issue last year. This is what 15 looks like in your book. However, it looks to me like it's 5x to the third. It is not. It is 5x times the cube root of the square root of 1 minus x squared. If it were 5x to the third, we couldn't do the problem. But like this is, you can do the problem.